That's what you're naturally made up of. Let's see if I can hit back here. Okay, there we are back at the periodic table of the elements. And so most of the ones that we work with in biology are going to be these guys right here in the green. Those seem to be the most prevalent for life on Earth. Bless you. When we see atomic structure, thinking about how those atoms are put together, we have the nucleus where we have the protons and the neutrons. So nucleus is in the center of the atom. In this case, we have a hydrogen atom. It's made up of one proton, which is designated by the plus, proton plus. We've got 0 neutrons and 1 electron, and the electron is designated as a minus. So neutrons are neutral, they have no charge to them, and then electrons are the negative, protons are the positive. Here you can see the difference between this hydrogen atom and the carbon atom. The carbon atom has several more layers of electrons. It's obviously got a lot more protons and neutrons there in the nucleus. And the forces of attraction between positive and negative are what keep these electrons, which are floating all around the nucleus, keep them attracted towards the nucleus, and so that they don't go flying off into outer space. So carbon atom has 6 protons, so 6 positives, 6 neutrons, so 6 neutrals, and then 6 electrons, which are in these orbitals or the shell that's all around the nucleus. So the electrons, as you can see, are floating in this electron shell, which is all around the nucleus. And this is what we picture that they look like, but it's actually floating in a cloud, and it's going so quickly that we would never be able to pick out an individual electron. Sometimes we see what's called an isotope of an atom. So atoms that have the same atomic number, which means they have the same number of protons, but have different atomic masses, are isotopes. So here we're talking about carbon 12, which is the most common. Carbon 13 and carbon 14 are what they start to degrade into. So if we look at our protons in carbon 12, we have 6 protons and 6 neutrons. Add them together, we get 12. In carbon 13, we have 6 protons and 7 neutrons. So add them together and we get 13. 6 protons and 8 neutrons, we have 14. And so you might wonder, so who cares? Why does that actually matter? So when I was Googling why do isotopes matter, I found a really interesting link, which I'll put up on the website, where it talks about food preservation. Your food is made up of carbon atoms, but when we want to preserve food, we need to radiate it so that the microbes die off. So any of your food that you get is going to usually be radiated food, like your apples, or if you think of your avocados. They're radiated to kill off those microbes, and it also makes it so that the seeds don't grow. So if you take an avocado and you pull that big giant seed out of the center and stick it in the ground, it's not going to grow, unfortunately. So we have to get our food from other people, or we have to get our seeds from the store. It's important in carbon dating. Carbon dating is how we tell how old rocks are, or how old fossils are, or things that are thousands of years old. So in carbon dating, we look at how much carbon-14 is left in an organism. It decays over time and becomes less and less carbon. So we can look back thousands, hundreds of thousands, millions of years and tell how old something is. Disease diagnosis, we can use radiation to tell about some of the diseases that we see out there, and then in treating them, anybody who's ever heard of radiation for cancer treatments knows that an isotope is very important, because radiation for cancer comes from isotopes. So those radioactive atoms that we talk about, they have this atomic nucleus that is not stable and that breaks down. They all break down over time. It just depends how fast it's going to break down. So they release this constant rate, a tiny high-speed particle carrying a lot of energy. And that's what radiation is getting those doses of energy that are shot at the cells, like in cancer, in order to kill them, or shot at the bacteria in our food in order to radiate it and make sure that it's not going to make us sick. So the way that that happens is by breaking down those nuclei of the atoms. So next we're going to talk about how those atoms come together. We first talk about how they break apart, and then we talk about how we fit them back together. So atoms can bond together to form molecules or compounds. And so they do this by forming, in this case, covalent bonds. We're going to talk about covalent hydrogen bonds and ionic bonds. So in the first type of bonding, covalent bonding, this is when the hydrogen atoms are most stable when they have their outer electron shell filled to capacity. So if we have this outer shell right here, they're going to be the most stable when they are filled to capacity. So this hydrogen atom has one electron, and this other hydrogen atom has one electron. They want to be stable at 2 electrons, and so what they're going to do in covalent is they are going to come closely together so that each one is sharing with the other one. And so covalent bonding is the sharing type of bonding. Some other examples that we see of covalent bonds, here we have an oxygen molecule. So the oxygen that we're breathing in the air all around us is not just O oxygen, it is O2, it's an O2 molecule. And so each one of these oxygens has its own electrons, and then it has 2 outer electrons that it shares with the other oxygen, and that's what makes it stable. So it's sharing these 2 so that each one can have their outer energy levels filled up. Here we have a methane molecule. We have our carbon in the middle, and we have it's CH4, carbon in the middle, and the 4 hydrogens around the outside. We've got our 2 here that are shared between the hydrogen and the carbon. 2 here are shared, 2 here are shared, 2 here are shared. And that's so that the outer valence electrons are going to equal the number 8. And only in the case of hydrogen do we see it equaling the number 2. In hydrogen, we have 2 that are shared. Here, we're going to have 8 around this one. We have 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen becomes stable. And then we have 1, 2, 3, 4, 5, 6, 7, 8, and that oxygen becomes stable. So that's kind of the magic number in chemistry, is the 8 electrons in that outer shell. And so lots of different ways that we can represent those, and sometimes you see them with the electrons, sometimes you see them with the types of bonds called a Lewis model. Here we have the ball and stick, which many of you probably played with, the little plastic beads that you stick together with the bonds. And here we have what's called a space filling model. If you had 2 of these right here, it kind of looks like a Mickey Mouse. So the next type of bonding we're going to talk about is ionic bonding. So ions are charged atoms. One of the most common ones that we talk about in biology is sodium chloride, or regular old table salt. So sodium chloride is a sodium ion that has 11 protons and 10 neutrons, so it's got a positive charge to it. The chloride ion has 17 protons and 18 electrons, so it has a negative charge to it. So it's basically going to donate this electron to the other atom. So whereas in covalent we see this sharing, here in ionic we see donations. We see give and take. And so here you can see that we have the one that we just talked about, sodium and chloride. So this is the way that they're going to look, because the opposites attract. The sodium is positive, the chlorine is negative. They're attracted to one another. So that allows them to fit together in this crystalline structure, which is why you get your cubes of salt, or it looks like a cube. And so they form this crystalline structure. The final kind of bonding that we're going to talk about is hydrogen bonding, and hydrogen bonding is found in water molecules. So whereas we had our covalent, where they're sharing, our ionic, where one is donating and the other one is taking, here we've got our hydrogen bonds that are formed between the slightly positive poles of the water molecule and then the other slightly negatively charged atoms. So that's why water is going to have the kind of the way that it acts. It's going to have its function is because of the way that these molecules are attracted to one another. So there's hydrogen bonding that's going to hold these two together. And we're going to talk a lot about water coming up here in the next couple of slides. So a molecule's shape is what gives it its unique characteristics. So why is all of this bonding important? It's important because it's basically going to give these atoms their molecular personalities. The shape determines the function. So we'll see things like taste and smell. Here we see that our brain, and you know, whenever you're eating something that really tastes really good, whether you're a sweet person or a salty person, if you like things that are sweet, then this glucose molecule that we have right here is going to fit into the sweet taste receptors. Or if you're a big salty person and you love potato chips or pretzels, you have this crystal of salt that's going to fit into the salty taste receptor. So your tongue has certain types of taste receptors which are genetically passed along from parents to offspring. Usually you're going to find these similar within families. And you either really like salt or you really like sweet, and some of us really like both. And so you've got these that you can taste, sour, bitter, salty, sweet. So your sweet might be your chocolate, or some of you might love candy. If you're a salt person, you're into dumping salt on everything. If you like bitter, that might be things such as grapefruit, or can anybody else think of a bitter flavored food? What is it? Lemon. Lemon does definitely, well, lemon I think is going to have more of that sour flavor to it. So maybe you like things that are really sour. Bitter, there's some people that when they taste things like Diet Coke, they get the aspartame and they get that nasty taste in their mouth, like, oh, this tastes really bitter. To me, that doesn't happen. I love the way that Diet Coke tastes, and so I may not have as many bitter receptors as you have. And then savory, does anybody watch the Food Channel or watch those cooking shows? Do you know what the savory taste receptor is called in those cooking shows? Have you ever heard of umami? Yep. Umami is the name of that savory. It's used a lot in Japanese cooking. So in talking about another way that molecules interact with one another, you've all been through the termite lab by now, so you've seen how pheromones work. So in the we may have a male moth or termite and a female moth, and this female moth is putting out these pheromone molecules, and this male gypsy moth says, oh, I detect those molecules, and so I'm going to go find that female wherever she is. In this case, it's saying that the pheromones could be 2 miles around the radius of this female gypsy moth. So they can detect these females from as far away as 2 miles just because of her sexual pheromones. So it'd be pretty sad if you were that lonely gypsy moth that was more than 2 miles away from the males, because you'd never get any visitors. So it's funny. It also makes me think about people that pour on their cologne in the morning. You ever been around somebody that you're like, wow, that's really, really smelly? Maybe they're trying to get as many mates from as far away as they could possibly find them. So thinking about our termite lab, this is the way that the molecules interact so that they can send signals from one to another.